I was talking about expansion cards and expansion buses, and the last one I mentioned was USB. USB, of course, was an external bus and something you plug in the back of your computer, and it had some definite advantages over the other types of buses that were internal, in that you could easily connect to it and disconnect rapidly, and it provided both power and signal to the external devices, and it was a fairly fast thing, especially the latest version, which is up to 4.8 gigabits per second, very fast. Now, they're related, similar to that is IEEE 1394. IEEE 1394 is also called FireWire, and it's very fast also. It runs up to 400 megabits per second, and its primary use today is for digital video, and sometimes hard drives and certain things. But it's not as popular as USB, and it may be that USB will sort of win out and replace it for a lot of things, but its niche seems to be in the digital video area. And it handles up to 63 devices. USB can handle up to 128 devices, or 127. And let's see, we have also some special expansion cards you sometimes see on motherboards. There's one called AMR, which is for modems. There was one called an ACR, or Advanced Communication Riser, that was used for multi-purpose cards that did a number of different things. And then there was one called CNR, Communication Network Riser. And for example, the AMR slot was used, or ACR slot, Advanced Communication Riser, was a multi-purpose card that was sort of an extension of the motherboard, and it provided multiple things like USB, it provided network card, maybe audio, modem, wireless, all in one card. So it was a special kind of slot, but you didn't see it too often. It's not real popular. Alright, and which of the following expansion technologies conserves the use of IRQs? Well, is it USB, MCA, AGP, or VESA local bus? And the answer to that is USB. IRQs are interrupt requests, and USB had the advantage of conserving that because it all uses one interrupt. So that solved a big problem that we've had in the past, which was too many devices or conflicts with the interrupts. Which of the following expansion card slots are placed closest to the CPU and memory slots? USB, MCA, AGP, or VESA local bus? Well, the answer to that would be the video, AGP, and VESA local bus, I suppose, too, but that's obsolete. The one that's really you see today that's next to the CPU is the AGP, because it's the video, and that requires a lot of data flow to and from. Which of the following parallel port standards supports bidirectional communication and multiple devices? LPT2, ECP, EPP, or EPT? Well, the answer to that one is ECP, and that's because ECP was the one that provided both directions of data. It could send and receive data, and it would provide multiple devices. You could have more than one device connected to it. It's not actually that popular. In fact, parallel ports all the way around are becoming obsolete. The EPP port, extended parallel port, is quite popular on computers that have them. It's used a lot because that uses two-way communication for things like laser printers. But the capability of having multiple devices on a parallel port, it really wasn't used that much. So it was a good idea, I suppose, but USB has largely replaced it. Now let me talk a little bit about system resources. What do we mean by system resources? System resources include things like interrupts, I/O ports, memory address ranges, and direct memory access. What do we mean by interrupts, or IRQs? Well, IRQs are a way of getting the CPU's attention. As the CPU is running, it would be nice for it not to have to stop what it's doing all the time and check various devices. In other words, it would like to be able to run whatever it's supposed to be running and not be bothered all the time unless it really needed to be. If you didn't have interrupts, what the CPU would have to do is continuously check all the I/O devices. It would have to ask the keyboard, do you have anything for me? It would have to check the mouse. It would have to check the hard drive to see if it needed attention. It would have to check the video card to see if it needed attention. It would have to check the modem and the sound card, and all these different things need attention from time to time. Well, without interrupts, that would take up a lot of the CPU's time. It would slow it down. It would keep it busy doing all these checks when it would really rather be doing, running programs. So that's what the interrupts are for. They're a way of tapping the CPU on the shoulder and getting its attention. And originally there were 8 of these, 0 through 7, but they added more later because that wasn't enough. That turned out that as people added more devices, although it was possible to share interrupts, it became awkward, and they added additional ones, and so there's actually now a total of 15 of them. 2 of them are shared because they call it cascading, which basically says that one interrupt feeds this other group of interrupts here, because the original design of the chip on the IBM PC, the CPU, was only designed to handle 8, and in order to be backward compatible they had to do a little trick here to make that happen, so they added additional by cascading them. Now, another type of resource that the motherboard has is called I/O port addresses, and these are called input-output ports. They're kind of like memory addresses, but they refer to different devices and the data associated with those devices. For example, here we have a list of the 4 different serial ports that you can have on a PC. I call them COM1 through COM4. Well, COM1 had an interrupt request of number 4, and it had its input-output address being hexadecimal 3F8 to 3FF. It had 8 different bytes that it would use to communicate with that COM port. So when the CPU wanted to send something out the serial port or receive something from the serial port, it would access these different bytes or locations, but these weren't in memory. These were in the input-output device itself. So when you wanted to output something, you'd output it to an address, or if you wanted to input something from that device, these were considered to be special addresses that were associated with the devices. And each device on a PC has to have its own I/O address. They can't be the same. They can't share them. I/O addresses have to be completely unique. Fortunately, there's thousands of them available. Now, that's not true of the IRQ. IRQ, there's only, on the original IBM, there was only 8 of them, and the ones we have today, there's only really 15 of them. So they have to share some of these. So like COM1 and COM3 shares number 4. That's not really a problem, because what happens is the PC CPU, when it gets an interrupt, knows that, okay, I've got an interrupt from COM4, I just need to identify who created the interrupt, and it can then do that by accessing the I/O addresses, and inside those I/O addresses there will be some bit that will be turned on or something to tell it which one of those devices caused the interrupt, and then it will then proceed to process that particular interrupt and service that device. Same thing here with COM2. You see, COM2 has a different I/O address than all these other ones, but it shares its IRQ with COM4. So again, if the CPU got a interrupt on COM3, it would go and look and see which one caused it, whether it was COM2 or COM4. Memory address range refers to a range of memory that a device shares with the CPU in the RAM memory space. And these are memory addresses. Some of the devices, like the video card, for example, would use a piece of the RAM memory for its own function. In fact, some video cards have built-in memory. Other ones use the main memory that the CPU uses on the memory modules. But whichever one it is, they still had to have some kind of address range, a place where you could write data to be displayed on the screen. You see, when something's to be displayed on a screen, what you're really doing is writing bytes and bits into a place in memory somewhere, and that represents a picture. It is then the video card takes that data and constructs a picture out of it. And that could be just as simple as individual bits representing pixels on the screen, or groups of bytes. And that is a piece of memory. And so each device that uses that kind of memory access has to have a range of memory settings that it is devoted to it. So if you had a video card, it would have a memory range settings. If you had two video cards, they would have to have different memory ranges because they wouldn't want to use the same memory ranges. They would confuse each other. Another device that uses memory ranges is the hard drive controller, because the hard drive can read data directly from memory and store it on the hard drive, or it can take data from the hard drive and write it directly to memory. That's called direct memory access, and it's something that requires a memory range. And so those are all examples of devices that use memory ranges. Now, associated with the memory range is direct memory access channels, DMA for short. DMA, there's a special controller built into the chipset in the north or south bridge that accesses the memory directly for devices. And there are 4 different channels that they can go through to do this, 4 different DMA channels. Fortunately, there aren't that many devices that use DMA, so we don't really need that many channels. So video uses one of them, hard drive controller uses one, and so there's not that many devices that out there that require DMA. But there are really just 4 channels, and that's considered a system resource. The DMA channel is the control of the flow of data to and from memory between the device, whatever that is. So these are all considered to be system resources: IRQ, IO ports, memory address range, and direct memory access. Now, how would you find such a resource? How would you find out about it on your computer? What would you look? Well, in order to show you that, I'm going to go over here to Windows, and we'll take a look at it right now. Here's how you get to this. So there's a couple of different ways. One way is you can go to the My Computer and right-click on it and click Properties. And if you do that, then you can then click the Hardware tab, and then there's a thing called the Device Manager. And the Device Manager lists all the different I/O input-output devices on there. So, for example, I want to look and see what resources does my video card use on that. And so what's called a display adapter, and I would click on that, and then I can look at the resources for that device. And there you see that this particular video card uses a memory range of E00000 to E0FFFFFF. Right? Well, those are hexadecimal numbers there representing the addresses that are available to that video card. And then we also have another resource here, I/O range. That's input-output location. So when the CPU wants to give a command to the video card or receive data from signals from the video card, it would access those I/O address ranges there to do that. So really there's 2 different ways that communication goes to and from the video card. Some is through the memory locations, the shared memory ranges, and the other is through the I/O address ranges. And of course the video and both the video memory range and the video I/O range have to be unique for a given video card. If you had another video card, it would have its own set of I/O address ranges. Alright, take a little break here.